When we talk about the rate of change of a function, essentially what we're asking is how fast is a function increasing or decreasing? We have two graphs plotted below, which we'll label as f of x and g of x. We'll start off with f of x, since it's a simpler case. If we want to understand the rate of change of this function, or how quickly it's increasing, we could look at selecting 2 points, say 3, 10, and 1, 0. And then we could calculate that rate of change by taking the difference in our y coordinates minus the difference in our x coordinates to get 10 over 2 or 5. When we carry out that calculation, all we're doing is finding the slope of a straight line. So that value m, if we were looking at constructing the equation of our graph in that y equals mx plus b form. So we found the slope of this line using 2 points, and we know that if we chose any other 2 points on that line, we would find exactly the same slope, because rate of change for a straight line is constant. It always follows the same pattern of going up 5 and over 1 to the next point, up 5 and over 1 to the next point. When we consider g of x, though, we can tell that's not the case. If nothing else, our function has an absolute minimum, also a local minimum, occurring at x equals 0. So our function is decreasing from negative infinity to 0, and then increasing from 0 to infinity. So that rate of change is no longer constant, and what we need to do is come up with a way to explain or identify the rate of change. So this function, which is 3x squared plus 5, we're going to talk about how quickly it's increasing over a specific interval. So we'll start off by considering a first case. We'll look at the interval from x equals -1 to +1. So at x equals -1 and 1, we have our points along the graph, and what we can do is just sketch a quick line connecting those 2 points. What we want to do is understand the average rate of change over this interval. So even though our function is decreasing over one portion and increasing over the other portion, we want to know on average what that rate of change was. Intuitively, we can look and see that what's happening from that beginning point to that end point is that our function value hasn't changed. So we could guess that our average rate of change is going to come out to be 0. In order to calculate that more directly, we could look at applying that slope formula to the line that we've constructed between these 2 points. So specifically, we'll look at calculating the difference in our y coordinates over the difference in our x coordinates, which would come out to be 8 minus 8 over 2, or just 0. So again, that matches up with our expectations. If what we have is a horizontal line, the slope of that horizontal line would be 0, meaning that over this interval, that amount of decrease essentially matched that amount of increase. So over that period, our function had a rate of change of 0, or an average rate of change of 0. If we look at a different case, say now from -1 to 2, we'll consider a different endpoint for our interval and sketch out a line connecting those 2 points. And again, apply the slope formula to those 2 points. So we'll look at taking g of 2 minus g of -1 over 2 minus -1 to get 17 minus 8 over 3, or 9/3, which is 3. Again, with a linear equation, with a straight line, we can talk about rate of change as a constant value, the slope. When we get into curved functions, curved graphs, we have to approach the problem a little bit differently since, again, we have a different rate of change occurring at different points. So we can define a specific interval to consider and then look at the average rate of change from one point to the other by calculating the slope of the line that passes through those 2 points. We can take this one step further and actually come up with the equation for the line that passes through those 2 points, which is a line we refer to as the secant line. In order to do this, we can start off with the average rate of change. That we calculated in case 2, and we'll refer to that as the slope of our line. So we can start off by constructing the equation y equals 3x plus b. So we know that the line passing through the 2 points, x equals -1 and x equals 2, has a slope of 3. What we don't know right now is the value for our y-intercept, that value for b. But we can find that by taking an x and a y pair that that line passes through, say 17 as our y coordinate, and -1 as our x coordinate, which is a pair that we already found. I'm sorry, that should be 2, not -1, which is a pair that we already found when we calculated the slope above. And then solving for b, we would get 11 is equal to b. So the equation for the secant line is going to be y equals 3x plus 11. So again, what we've found is the equation for the line that passes through these 2 points, and it's the slope of that line that tells us the average rate of change for that function over that interval. Let's look at doing the same thing one more time with the function f of x equals 6x squared minus 8. In this case, we want the average rate of change from -5 to 7. So we'll start off by finding the slope of the line that passes through those 2 points by taking the difference in those y values, or our function values, minus the difference in our x values, which would give us 286 minus 142 over 12, or a rate of change of 12. So this is our average rate of change for that function. Over that specific interval from -5 to 7. And then we can construct the equation for the secant line by again using that result from part A as our slope and solving for our unknown y-intercept. Using the values that we generated in that step above, we can plug in y equals 142 paired with x is equal to -5, and then solve for b, which in this case would give us b is equal to 202, meaning the equation for our secant line would be y equals 12x plus 202.